All right. So yeah, we got a little bit of time to do this one the other day. We drew the forces, right? So going over the hill here, we can model this as a circle. And then we said the normal force was going to be pointing up on you, and then your weight was going to be pointing down on you. Why is the weight bigger than the normal force? Because you're accelerating which way? Downward towards the center of the circle. So if you're accelerating centripetally, that means in the perpendicular direction of motion, that you're going to have a net force in that direction, because F net equals ma. So whatever the direction F net points, that's the direction the acceleration points. Yes. Okay. So, all right. So we got. So I'm going to apply the second law. That's what always comes next. You draw free body diagram. You apply second law. And F net in this case is going to be
centripetal force.
mg minus Fn. Why is mg positive? If it points towards the center of the circle, it's positive, right? That's the convention we're going to use. If it points towards the center, it's positive. If it points away, it's negative. It has yet to steer me wrong, so we'll see. Now, once again, well, let's do a couple things. First off, what type of acceleration do I have here?
Centripetal.
This is centripetal I'm looking at, so it's v squared over r. I can replace this with. And then, well, I got mg here. What gives you the feeling of weight? We talked about this. The normal force does, right? Because again, you sitting right there, feeling that it gives you that feeling of weight. Once again, I can jump off of, jump off of the building, and I feel quite light until, yeah. Oh, we're even going to see what, like, we're going to see what the buoyancy forces mean when you float in water. You feel lighter as well. So yeah. Okay. Normal force gives you the feeling of weight, and we want to feel 1/4 of the weight. So that's basically just going to be 0.25 mg. Come on. And while I did say find out your weight if you were sitting in the car, so you could use your mass, but what do you notice happens to the mass here?
Cancels out.
It cancels out. So whatever this solution is independent of mass. Okay. So that means I'm going to have g minus 0.25 g. What's that?
0.75 g.
0.75 g. All right. You guys are more awake than last period. Oh, they were just like, huh? So, okay, we got 0.75 g, and then, we got the speed, we're trying to find the radius, so I can just isolate the radius, multiply the radius by both sides, divide by 0.75 g, that'll give me r equals v squared over 0.75 g. I know what baby g is, I know what v squared is, or I know what v is, so I can square it, get the answer. Yeah. All right. Correct. Which means you would have to go. That's a good point right here. The faster you go, do you experience more weightlessness or less weightlessness? More weightlessness, right? So if you wanted to feel like what Ramon just brought up, if you felt like 0.7, if you want to feel 3/4 of your weight, would you have to go faster or slower?
Say it one more time.
Slower. Yeah, you'd have to go slower. So the radius being the same, this would be 0.25, this would end up being 0.25 g, and if I multiplied over here and solved for this, once I got the radius, then I'd have to go slower in order to experience that. So the model is fitting what our intuition would feel. Okay, other questions? All right. Who's got their license? Or just got their license?
Oh, just one?
Wait, Mr. How come like
Beginning of the hill?
yeah.
Speed?
Alright, okay. When you get to curves.
You do, that's true, yeah.
Because like, doesn't it feel like there's, you feel heavier here?
If I don't, that's fine.
Yeah,
Yeah,
yeah.
this makes sense.
So we're talking about the moment at the very top,
okay.
at that very moment. Yeah. You got your license? All right.
Because I remember like, I think we're somewhere here.
I'd be like,
So we got Jackson inside his car. He's driving. He's driving on. I think I made this number up because the solution ends up kind of making me a little silly, but so he's driving in a circle of a radius of 10 meters. So driving in a circle, radius 10 meters. There's his speed right there. And the coefficient now. The coefficient of static friction between the road and his tires in this case, maybe it's a dirt road or something like that, is 0.7. The radius is 10 meters, and again, here's an above view, so this would be you looking down and seeing Jackson. For some reason, he's just going in a circle.
Donuts.
You know, hey, wasting gas, right? Because screw the environment. You know? So, yeah, he's going around like that, right? And so, but what this perspective is this perspective is if you were looking like this at it. So he's going around like this. And then here I'm marking as the center of the circle. What I'd like you to do, we're going to find out what's Jackson's maximum speed he can have before slipping. So what's the fastest Jackson can go in these conditions before he starts to slip?
Wait, so mu is rolling friction?
Mu is static friction.
Static.
So what I want you to do right now is draw a free body diagram of the forces acting on him on this diagram. So kind of make that diagram and then draw the forces acting on him. Please.
So are the wheels just not there? He's in park. Static means you're standing still. Static means you're still.
That's so weird.
How are the wheels still?
When you brake,
When you're turning in a
Oh,
circle,
you're
right?
braking?
No, because he's turning, right? He's constantly going in a circle. So that means the force that he's going forward has to overcome the force. That's what drifting is. That means
So
your back end is
you
going
want-
faster than your front end.
So we're seeing where
Yeah, so at what point does he?
at what speed does he have to do something?
Yeah.
That'd be great. Okay, okay. So your S net has to be 0. Your S net. Your axis. Just think about it. Your friction force. That makes sense.
What is that? Call it. Force the call.
How much is Jackson
So yeah, what forces we got here?
Friction force.
Oh, starting with the friction force. What direction does the friction force point?
Towards the center.
Towards the center.
I got it.
What kind of friction force is it?
Static.
Static friction. What other forces?
MG.
Force of gravity, mg pointing down, and the normal force from the road pointing up. So, alright, use the second law and figure out what's the maximum speed that he has to go. I do have that.
You're looking for the maximum velocity. You're not saying like signal velocity.
But you're not going over a hill. You're going in a city.
Yeah. Alright, so what does that mean then?
Your mom.
Oh, plug in everything.
That's exactly my question. I don't know what I
B squared.
What?
Is this the range?
Mr. Foreigner.
Hey, you could. What are you gonna do? You know this one? Right?
So basically, you have to solve.
R is 10.
Super Mac.
Yeah.
We're almost done with the book. We're almost done with the book.
That's not almost done.
We basically finished 6 of 9.
For the vertical direction?
Oh yeah.
Because 1, 2, 3, he already made us for the first 2 weeks.
Well, yeah, there's this. So, an F in this case is which of these forces? The friction that's causing the acceleration.
Honestly, it's a great use of it, but if you're not caring about that,
Sure.
it shouldn't be.
250.
Oh wait, no.
And you're not gonna go into like. It's just GE.
Let me do that unit.
All right, yeah, fair enough. Don't forget Jackson's math.
Reads so much.
250? Oh, I was gonna say kilograms? So, all right. Gee whiz, we just drew a free body diagram. What's always next?
Second.
Second law, right? And I can do this in the y direction and in the x direction. What is F net in the y direction? Fn minus Fg. So the normal force minus mg equals, what's the acceleration in the vertical direction? 0. Zip. So that basically gives me the relationship that the normal force is equal to mg. And so I got that relationship. What about in the horizontal direction? What's the net force? Oh, sorry, FS I called it. Sorry, FFS. Force of static friction. And if we're talking about just before slipping, what kind of static friction force is this? That's maximum static friction force. Because this rule, which we're going to have to use, only applies in static friction for static friction max. Kinetic friction, you can use this anytime. Anytime. But static friction, this only applies for static friction max. All right? And it equals the mass times the acceleration. Is this object accelerating?
Yes.
Yes? So Jackson in his car, meaning. And the acceleration is?
V squared over R.
V squared over R. All right. And so I basically got this relationship from this. So, well, I'm looking for the speed. Do I know his mass? And the car's mass? It's going to be both him and the car? No. Do I know the radius?
Yeah.
Okay, I got that. So, and then I don't know the static friction force. So I got to relate these two somehow. How can you always relate those two?
Coefficient times Fs.
Yeah! I can use that Fs max equals the coefficient of static friction times the normal force. And all the normal force, that's all this. I can plug that in there. And FF, the friction force, maximum static friction, I can plug that in there. Let's see what this does. M V squared over R equals the coefficient of static friction times mg. And yeah, what cancels out?
Yes.
So who cares what Jackson's mass is? I mean, we care. Right? Because it doesn't matter. It cancels out. And so we're solving for V. So let's see. I'm going to multiply both sides by R. So it's going to be V squared equals R mu S times G. And then you got V equals the square root of R mu S G. Or rather, so the speed is the square root of rug. And there you go. So the square root of rug.
Say that.
Rusk.
No, try saying it with like. Say it.
Questions, comments, concerns on this one? So I'm fairly certain. I hope I've done. I've assigned a problem like this on your homework. Yeah, because I have seen questions like this on the APC exam. These are basically just turning problems. Yeah.
Yeah. 26 years of age is Dmitriev. All the Belarusian volunteers who are in the centre of the track helping out with all the organisation. They were jumping up and down with delight when he got himself through to this final. I think he might be a very popular winner.
Yes, I don't understand why this is an Olympic sport.
Boxer isn't happy with Dmitriev being in second place. Dmitriev looking absolutely poker-faced.
And trust me, I've watched this Olympic sport before. I want to be like, why are they going so slow?
Well, these two riders make this look very easy, but you have to keep the pressure on the chain all the time. especially on the steep bank. You go this slowly, it's very easy to just slip down.
Yeah, look at that angle. Good, yeah.
Television doesn't really show just how steep this track is.
You've got the high ground energy.
Dmitriev says it's going to be a different. Russia starts to accelerate. Let's chance him where he wants it.
Why is it only 2?
This is going to be an interesting competition here. Dmitriev kicks the bike down to the bottom. Now he moves a little bit. He's going to push the lead. So he holds him right at the track. Dmitriev now turns on the heat. Then he used his slipstream to good effect. He was off the wheel pretty late actually. And he powers his way through. Then very, very close.
Oh my God!
Almost a little bit of a warning. And he wins it by around about a win.
Wait, they slow down. Look at the They're gonna hit each other, right?
No.
Oh, there's no description or press so hard.
Press so hard.
No, it's called like volodrome.
Because it says
Oh, that was a lap.
Well, alright.
Yeah, I know. Wait, this is Velodrome.
It's like the first
Christian also said I legit thought it was
Velodrome.
Volodrome?
Velodrome.
Velodrome, that sounds right, yeah, yeah. So, okay, we're gonna solve a problem like that.
Velodrome
I'm
problem?
gonna go home.
Wow. Oh no, I saw this one while I was looking for the chart. I was like,
Oh, the one that is on a ramp?
yeah, the car, when the car is turning, and then you have to like, you have to calculate with the.
So, we are gonna do a couple things. So, let's see, we're gonna say the radius. So here's the bike, they're going like this. They're going this way, and around, and this way, and around. Here's the center of what they're doing. So they're going in, then out. And in, okay? Here's the bent curve. We're going to assume no friction.
Wait, wouldn't they just slide
They're gonna
off?
fall.
They would not fail.
Wait, but there's no friction to hold it up.
But they fall.
But they would want to go. They would want to go out of the circle, basically, right? If you have a circle, the inertia of the object wants to go out.
Oh, so we're assuming it's already in motion.
The normal force.
Yes, it is. I'm sorry.
I thought it was just standing.
Going very
I
fast.
thought they were gonna go super slow.
No friction.
They're just like slide down like.
So they would want to go out, but the bent curve is going to keep them in. So what I want you to do right now is draw a free body diagram on the forces acting on the velodromers. Velodromer.
Oh, now we have misbehavior vectors.
Yep.
Great.
Great.
Wait, are you assuming it's like a dome? It's like a circle? Like a semicircle?
Bro, look at the picture.
You just we're
Bro, I can't see a semicircle through that. I just see a line.
let's say it's like this thing,
What's the force
where
acting on the
the
center?
person's here, so we're modeling the circle
Oh,
like
no,
this.
there wouldn't be no force.
Okay.
Right? We're saying that that curved part is basically just a circle of radius.
It's just like the video we watched, right? There's a pit?
Correct.
Why?
Okay, got it. I had normal force, I had gravity, and some of
Oh, yeah.
What's the angle?
She watched the Gold Class.
Just theta, yeah.
They lick the salt off the little. I was like, I know.
Oh shoot, yeah, huh?
This is actually not that
Keep it the same.
I know.
So, alright, seems like people got their free body diagrams. What forces are acting here? Normal force points perpendicular.
You're.
Perpendicular to the surface always.
MG.
And the weight which points
Down.
down. We're gonna assume they're moving at constant speed. So while there is gonna be a force of friction from the bike that's pushing them forward, there's gonna be wind that's gonna pull them back, and that keeps them at constant speed right now.
Nice.
So, well, that's the assumption we're gonna make. Now, typically when you've seen these ramp problems, you go, oh, I gotta tilt my axis and all that type of stuff. However, how many vectors do I have? Two. So if I tilt my axis, I'm just tilting it for tilting's sake, right? So that's that. It's actually better just to keep your axis where it is in this case. So if the object is sliding up and down the ramp like this, okay, then you could tilt your axis or something like that. But here, I'm just actually going to break up. So I only have one misbehaving vector. Which one is it? Fn. So I'm going to split that into here, f and y, and here, which is f and x. Now the question is, how do I get theta in here? Well, I already know, well, if I know theta is this, what's this then? Theta, right? Because I got parallel lines,
Nice.
segmented, so that's got to equal that. What is that, alternate? Interior angle, sounds good. That sounds like a legit one, yeah. By definition, normal force is perpendicular to a surface, so what is this?
90 minus. Oh wait, 90 minus.
90 minus theta, right? Then what about this?
That's theta.
That's theta, yeah, because this is perpendicular as well.
Wow.
So that's going to be 90 minus theta. So the 90 cancels out, I just get theta left over. So that's your theta right there. So go ahead, see if you can do it. Solve for the speed of basically the minimum speed you would need in terms of the radius and theta.
Oh my god.
Oh, your God.
Wait. Oh, that's nice.
No, 90 minus, just use theta.
Wait, just use data?
Yeah, just use theta.
Okay. So it's not 90 minus. Data 1 data.
But you're solving for speed.
No, for the y. Stop finding the y. Well, you can substitute mg minus.
That's a problem with data.
So R over, I mean, that's now. So you do RG sin theta. Yes.
We're looking for.
These are both cosine?
Because that's the only thing with the net.
So this one is, if you put it on the triangle, is that gonna be opposite or adjacent?
Nice.
But, okay.
No, you can use sine data.
Wait, so we're not using 90 minus data?
No, I would not use it. I would just use theta. The whole thing is just to prove to you that that theta down there is that theta up there.
Oh, okay.
Square root of RG sin
Sine theta is same thing as cosine 90 minus.
Oh, use 90 minus theta. Why is everybody using 90 minus theta?
I don't want to use
Why would you
tan
do
theta,
that?
I told you.
So you don't need 90 minus theta. That's basically your free body diagram. So just use that theta between M and Y.
Yeah, why would you?
So sinus theta be or F and
Oh
X.
no. Breaker stacks. Oh my.
Think about it, like
Context is I'm gonna use more than one. Not for using wood inside. Have you ever seen Carrot Clarinet? Pretty late.
So it's basically you're using
I agree with this.
Oh,
And then the normal course along Y though. Yeah.
So you're gonna have to say cosine cosine sine sine.
Oh yeah, that's exactly. You mean
You just took it to Cal, right?
Oh, you didn't do that shit yet. Nah.
F and X though. If you look at that angle,
And it's gonna be like cosine sine.
triangle. What is it? So if it's right, what would you use sine or cosine?
It's all gonna be stuck in here. So what are you doing this?
So, yeah, guys, this thing split up here. F and X is basically that part of the triangle. Are you going to use sine or cosine for F and X? Sine, yeah. I would use sine for F and X and cosine for F and Y.
Disgusting. Disgusting.
I don't like sine either.
It's cosine or nothing for you?
Just only cosine.
So wait, you got cosine 90 minus theta in there?
Yeah.
Why would you do that?
Sine is no. Tangent is. Join the cosine.
Yes. Yeah, but this is b squared over r. Wait, whoa. That's the acceleration, but it'd be the acceleration only in the x direction. There is no acceleration in the y direction.
I use the inverse.
Oh wait, that makes sense.
I use a derivative of the inverse.
Yeah.
I use it.
So, yeah, I'm not going to solve this one because this one is extremely similar to one of your homework problems tonight.
Oh, yeah.
It's not a Banks curve necessarily, but it's someone on a bike again that's tilted. I think, did you come to me about that?
Yeah.
And you got the same answer again.
Brain cells.